So another area that is of great interest, and we're seeing a lot of research activity, is quantum computing, of course. And from our perspective, it's the materials issues that are crucial for quantum computing. Can you describe the technology underlying the quantum computing effort and why materials are critical for this?
So there are numerous different hardware approaches that people are taking. I want to focus on one that is common to several industrial efforts, which is based on Josephson junction technology, low temperature Josephson junction. And the idea is as follows. You know we have quantum states, right, in an atom, right? That's what we think of as quantum states for an electron and atom. The idea here is to create a resonator that would act sort of like an artificial atom. Okay? So what we do is we make a circuit that consists of a capacitor and an inductor, and that's going to resonate. But there's a big problem with that, which is if you have just a resonator conductor circuit, it has evenly spaced levels, right? Just a harmonic oscillator. And suddenly you're not dealing with something with a 0 or 1. It's, if you excite the thing, you're not going to know which of the states it's in, right? So we want something that's just confined to two different states, sort of like an electron going between two different states. So we put in the Josephson junction, and that's nonlinear, and that spaces out the states, all right? Makes them nonlinear, so now we have the two lowest lying states are at a discrete frequency, and we can make our artificial atom, okay? Now, the way this is done, to actually program it, is you excite it with microwave frequencies and put it in some superposition of states and let those propagate. I will come to materials in this, okay?
Sounds good.
Okay, so I just said microwave states, all right? So now these mugs, these are kind of nice mugs. Can I microwave these mugs, do you know?
I think so.
You think so? This is because the MRS uses high-quality ceramics. Yes. Now, if I put this in a microwave and it's not the right kind of mug, what happens? Question to you.
It sort of heats up tremendously.
It heats up, exactly. Yes. So what's going to happen, if we have the wrong ceramic or the wrong material there, it will absorb the microwaves, right? Now, I just told you we're storing the information in this qubit as a microwave field, right? So what's going to happen is if there's anything nearby that can interact with with that microwave resonator, you will lose information. It will be in the coffee mug instead of the computer, right? This is very bad situation. So in fact, a lot of what's going on now is a struggle to improve coherence lifetimes and to fight against defects that limit coherence lifetimes. They're known as two-level systems. We don't know for sure whether they're two-level or not. That's just an early model for them. But a lot of the work in terms of choosing materials, integration routes, and so on and so forth, in creating the qubit is struggling on how to avoid those sorts of losses and give a longer lifetime. Okay?
So going a bit further, what are the challenges for material science, and where should our efforts in materials be focused on to move the field forward?
So there are a lot of different things going on here. One is what I just described that some of the big laboratories are grappling with. There are also opportunities in terms of different designs for the circuit. We favor, we're mostly working on something called a transmon design, but we know there may be other designs that may turn out to be have advantages. There are also a lot of alternatives to the sort of technology we're pursuing, and it's important to have a diverse number of efforts. There are people who are working on things like spin centers as a way of making a quantum computer, ion traps, a lot of different approaches going on. It's important that we keep looking at all these different things, because one of those could turn out to be a superior technology. We wouldn't want to miss that chance.
Right.
Now, another completely different angle on this involves what do you do with a quantum computer once you have it, right? And there's a lot of effort goes into thinking of algorithms that can take advantage of quantum computers.
Mhm.
And I'm sure that there will be opportunities for materials discovery and for material science, and the people who develop those algorithms first are going to reap the rewards.